So to work with substances in aqueous solution, that AQ state of matter in our chemical equations, we are going to measure the amount of solute dissolved in a solvent. So concentration is a quantitative measure of the amount of solute dissolved in a known quantity of solvent. There are many ways to write concentration. You can write it using percents. So you could say there's a percent of hydrogen peroxide over water. That's how you'll see hydrogen peroxide if you buy it in the pharmacy. It'll be 3% hydrogen peroxide. So that means there's 3 grams of hydrogen peroxide for every 100 grams of solution or water. All right, you can also write it in parts per million. When you have a very, very small concentration, you'll see it written in parts per million. There's 1 part of some solute in 1 million parts of solution. And then we also write it in molarity. The most common unit of concentration that we use in the general chemistry lab is molarity. So molarity is the amount of solute in moles divided by exactly 1 liter of solution. So this is our calculation. Molarity equals moles of solute in 1 liter of solution. Missed an L, sorry. All right. So you can think of molarity as a conversion factor for going between moles and liters, just like we had the molar mass to go between grams and moles, and vice versa. Now we have molarity to go between moles and liters, and vice versa. So when we report a concentration, we report it in brackets when we're talking about molarity. So HCl in brackets equal to 0.3 means that there is 0.3 moles of HCl dissolved in 1 liter of solution. We also say the concentration is 0.3 molar. To determine a concentration in units of molarity, first you calculate the amount of solute present in moles, and then you divide by the volume of the solution so that you end up with moles per liter. All right, so let's practice. A student weighs out 9.62 grams of manganese nitrate and dissolves it and transfers it into a 250 milliliter volumetric flask, and then dissolves with 250 milliliters. So calculate the concentration of manganese nitrate in that solution. So our molar mass for manganese nitrate is 178.95 grams per mole. So when we take 9.62 grams, we're going to divide it by the molar mass so that our mass is on the bottom and moles are on the top. And that's going to give us 0.0538 moles. And now we want to take the amount in moles and divide it by our volume. So our volume is 250 milliliters, but we want that to be in liters. So 250 milliliters times, there's 1,000 milliliters in 1 liter. So we're actually going to divide by 1,000, and that'd be 0.25 liters is our volume. So we divide by our volume, and our molarity, our concentration, is going to be 0.215 molar. All right. So with these molarities and concentrations, we can also find the concentration of specific ions using ionic compound formula. For example, we have the formula calcium chloride. So for calcium chloride, calcium is a 2+ ion, and chloride is a 1-, so we need 2 of them to balance our charges. So let's see what happens. If we have a 0.344 molar calcium chloride solution, then that means there's 0.344 moles per liter of calcium chloride, and for every 1 mole of calcium chloride, there are 2 moles of chloride, 2 moles of chloride ions. So there's actually 0.688 moles of chloride ions in the same amount of solution. So our concentration of chloride ions is twice as big as our concentration of the ionic compound and as our concentration of calcium ions. So if you look at this diagram here, you can see that there are 1, 2, 3, 4, 5, 6, 7, 8 chloride ions and only 4 calcium ions. So that comes from both our ionic compound formula and our properties of concentration. Okay, so let's see what else we can do with that. So in the lab, a student adds 22.5 grams of cobalt sulfate to a 250 milliliter volumetric flask and fills up the flask with water. We want to calculate the concentration in moles per liter of cobalt sulfate, the cobalt ion, and the sulfate ion. All right, so cobalt sulfate, so cobalt is 2+ because of the 2 in parentheses, and sulfate is one of our polyatomic ions with a 2- charge. So when we combine them, we just have cobalt and sulfate with no subscripts for our ions. So the molar mass of cobalt sulfate is 154.996 grams per mole. So if we have 22.5 grams of cobalt sulfate, then we divide by our molar mass, so we can cancel out grams, and we find we have 0.145 moles of cobalt sulfate. Okay? And for cobalt sulfate, we don't have any subscripts, so cobalt and sulfate both have the same concentration as the ionic compound cobalt sulfate. So we have 0.145 moles in 250 milliliters, which again is 0.25 liters. So our concentration is 0.581 molar for the sulfate ion, the cobalt ion, and cobalt sulfate because we have the same number of uh, ions for both ions in our compound. All right, so concentration in units of molarity can be used as a conversion factor to convert between the amount of solute in moles and the volume of solution in liters, just like we said before. So we want to go between moles and liters. So, for example, we want to calculate the volume of a 0.242 molar barium hydroxide solution needed to provide 3.2 grams of barium hydroxide. So barium hydroxide has a molar mass of 171.34 grams per mole. So if we have 3.62 grams, then we want to divide by our molar mass. So that we cancel out our grams and end up with 0.02113 moles of barium hydroxide. And now, if we have 0.02113 moles, and this up here, our 0.22 molar, is 0.242 moles per liter. Molarity always means moles per liter. So we cancel out our moles, and we're going to end up with 27.3 milliliters, or 0.0873 liters. All right. So now we just converted between grams and liters using both our molar mass and our concentration. All right, so calculate the mass in grams of potassium acetate that must be added to a 300 milliliter volumetric flask in order to prepare 300 milliliters of 0.225 molar aqueous solution. So potassium acetate. Acetate is one of those polyatomic ions that I said you might want to remember, but in case you don't, it's our organic molecule, CHCOOH. And we write it that way because its structure looks like this. So you can see the COOH here and the CH3 here. Anyway, this is our potassium acetate. Oh, I'm sorry, acetate doesn't have the hydrogen on the end. That's where the potassium goes. Okay, so our molar mass of potassium acetate is 98.15 grams per mole. And if we want, so we want a 300 milliliter solution, which is the same as, I'm going to move my decimal point over 3 places, get rid of our milliliter, make it just liters, times 0.225 moles per liter. Means we need, means we need 0.0675 0.15 moles of potassium acetate, which I'm going to erase. 0.0675 moles. So now I'm going to multiply by the molar mass, which is 98.15 grams per mole. So that must cancel out. And we find that we need 6.63 grams of potassium acetate to make that solution. So you just want to keep track of all your units so that when you multiply, you can cancel things out and end up with the one that you're looking for. So mass in grams. All right. So making solutions is one of the most important skills learned by chemists. So you want to prepare a solution with a known concentration. This process has two parts. First, you need to calculate all your quantities that are going to be combined. You want to know exactly how much of everything to add before you do anything in the lab. Then you need to correctly prepare the solution in the lab. So there are two methods for preparing solutions with in the lab. There's direct addition when you want to prepare a solution with a relatively high concentration, and there's the dilution method when you want to prepare really low concentration solutions. And all of this glassware in this picture should look familiar to you from your time in the chemistry lab this semester. So we have Erlenmeyer flasks, we have beakers, we have volumetric flasks, those ones that just have the little marking on top that tell you exactly how much to add. We have graduated cylinders. We also have a burette, which you guys didn't get to use yet, but you would have used in experiment 11. And we have some of these pipettes. There's a graduated pipette and a volumetric pipette right here. All right, so those should all look familiar to you. And unfortunately, you won't get to make any solutions in the lab from here on out, but we'll tell you how you would have and how you will if you continue on to Chem 120. All right, so a student wishes to prepare 250 milliliters of a 0.164 molar ammonium nitrate solution using solid ammonium nitrate in a 250 milliliter volumetric flask. So what is the process? So let's see. So we have 250 milliliters. We're going to have 250 milliliters of solution, which is mostly 250 milliliters of water plus our solid. So let's see. If we have 250 milliliters, I'm going to move my decimal point. That's the same as 0.25 liters. And we want to make a 0.1 molar ammonium nitrate solution. So let's find out how many moles of ammonium nitrate we need using our concentration. We multiply by our concentration because we have moles per liter. So our liters are going to cancel out, and we're going to end up with 0.041 moles of ammonium nitrate. So ammonium and nitrate are both two of our polyatomic ions, you should remember. So ammonium is a +1 and nitrate is a -1. So when we combine them, we don't need any subscripts on our ions, and it just looks like this. And our molar mass of ammonium nitrate is 80 grams per milliliter, grams per mole. So if we want to find out how many grams of ammonium nitrate, or solid ammonium nitrate, we need to add, we're going to take 0.041 0.041 moles and multiply by our molar mass, 80 grams per mole. So we cancel out moles and we end up with 3.28 grams. So our process is going to be measure out 3.28 grams on a balance, add that mass to a volumetric flask, and then add water slowly until we get to 250 mils of solution. All right. The dilution method is used when we want really small concentrations of our solutions because it's really hard to weigh out small amounts of our solute with great accuracy. All of our balances are not accurate below, I'd say, milligrams of our solids, and sometimes you want to measure out a milligram at a time, which is not very accurate on our balances. So the easier way to make these solutions is to make a more concentrated solution with a known concentration and then dilute it. So it's just like if you make lemonade and it's too strong, so you add some water to dilute your lemonade. So we are going a concentrated solution with a known concentration because it's easier to weigh out a larger amount of our solute, and then we're going to dilute it down by adding more water. So the thing to note here is that the total amount of solute in moles is the same in both the measured amount of the concentrated stock solution and in the final dilute solution. So what we can do with that is we know that molarity is the moles of solute over the volume of solution. So that's the same as saying that the moles of solute, if we multiply by volume on both sides, is equal to molarity times volume. And if we know that the moles in both of our solutions are same, we have the mass times the volume of the dilute solution is going to be equal to the mass times the volume of the concentrated solution, just because we're going to have a small, for our dilute solution, we'll have a smaller concentration and a larger volume, whereas with our concentrated solution, we'll have a larger concentration and a smaller volume because we're only taking a small portion of our concentrated solution when we dilute it. So if we get rid of the stuff in the middle, because those moles of solute are the same, we end up with a nice little equation that relates the concentration and the volume of your dilute solutions and your concentrated solutions. So let's see what we can do with that. So in the lab, a student dilutes 20.6 milliliters of 8.5 molar perchloric acid to a total volume of 250 milliliters. All right, so this is our concentrated solution. We take a small amount of it, so we take 20.6 milliliters of our concentrated solution, which is 8.5 molar, and we dilute it to 250 milliliters. So we want to find our final concentration. So this is the smaller volume and this is the larger volume. So this is the larger concentration. So this is going to be a smaller concentration, so that you can check yourself at the end. It should be smaller than 8.5 molar. All right, so to do this, we want to convert into our liters because we're multiplying by moles per liter here. So I'm going to move my decimal point. So 0.0206 liters times 8.5 moles per liter is going to be equal to 0.25 liters times X, our unknown concentration. So you want to multiply these two, and then I would divide both sides by 2.25 liters to get X by itself. So that's going to cancel out, and we're going to end up with a concentration of 0.700 molar of our perchloric acid solution. So it's a smaller concentration. It's diluted from our original 8.5 molar solution. Okay, so now we're going to talk about stoichiometry. So the stoichiometry that we learned previously is going to work the same way here using solutions and concentrations. So previously, we were able to convert between grams of grams of A to grams of B using our balanced reaction and our mole to mole ratios. So now we're going to use volume and concentration to convert between volumes of reactants or products, concentrations of reactants or products, and so on. So here's an example. If we have this reaction and we want to find out the volume of 0.5 molar HCl that reacts with 5.6 grams of calcium carbonate, we are going to do this using solution stoichiometry. So first, we balanced our equation. So this is our balanced equation. We see that there's 2 moles of HCl for every 1 mole of calcium carbonate. So first, we have a mass of calcium carbonate, so we convert that to moles like we did in our previous chapter. And now we're going to use our balanced equation to convert moles of calcium carbonate to moles of HCl in our 1 to 2 ratio here. And finally, we're going to use that amount of moles of HCl and our concentration, our 0.50 molar HCl, to find the volume. Okay, so here's an example. We want to calculate the volume in milliliters of 0.415 molar nitric acid needed to react completely with zinc carbonate in a gas-forming reaction. So you guys haven't learned about gas-forming reactions yet, so I'll just tell you what this reaction will be. So we have nitric acid and zinc carbonate, and a gas-forming reaction almost always forms carbon dioxide, and you can tell because it's got carbonate as one of its reactants. So we're going to form carbon dioxide. We're also going to form water, and our final product is going to be zinc nitrate. So zinc is a +2 cation. Carbonate is a minus 2. So we didn't need any subscripts with zinc carbonate. But nitrate is a minus 1, so we did need a 2 subscript here. So let's balance our reaction. So we have 1 zinc on the left, 1 zinc on the right. So that's good. We have 1 carbon on both sides, so that's good. We have 2 nitrogens on the right, so we need 2 nitrogens on the left. So we put a subscript in front of our nitric acid. And now let's see, we have 3 oxygens from zinc carbonate and 3 from nitric acid times 2 gives us 6. So that means there's 9 oxygens on the left. Over here we've got 2 from our carbon dioxide, 1 from our water is 3, and then 6 from our zinc nitrate because of our 2 subscripts on the nitrate. So that means we have 9 oxygens on the right. Perfect. And lastly, hydrogens. We have 2 hydrogens on the left and just 2 from water on the right. So we are balanced. We just needed that one coefficient of a 2 in front here. So let me erase. So we have 2 nitric acid molecules plus 1 zinc carbonate forming 1 carbon dioxide molecule, 1 water molecule, and 1 zinc nitrate molecule. All right, so we want to find out how much nitric acid is needed to react with 8.8 grams of zinc carbonate. So our molar mass of zinc carbonate is 125.4 grams per mole. So 8.8 grams divided by that molar mass. So we can cancel out our grams. Gives us 0.0702 moles of zinc carbonate. Should be 3, sorry. And for every 1 mole of zinc carbonate, we have 2 moles of nitric acid, thanks to our balanced reaction. So I'm going to multiply this by 2 and see that we have 0.140 moles of nitric acid. All right, so now we have moles of nitric acid and a concentration. So we have 0.140 moles of nitric acid. And I'm going to divide by our molarity so that I can cancel out moles and have liters on top. So moles cancel out and we end up with 338 milliliters or 0.338 liters of nitric acid was needed to react with 8.8 grams of zinc carbonate. All right, great. So here is a overview, a summary in graphical form of solution stoichiometry. So if you have grams of A and you want a volume of solution B that reacts with grams of A, which is what we did in the last problem, we used our molar mass of A, our molar mass of zinc carbonate. To find the moles of zinc carbonate, we used our balanced equation to find the moles of nitric acid, and then we used our concentration of nitric acid to get to our volume of nitric acid that was needed. So that is one way you can go about this. This is what we did previously, grams of A to grams of B. We can also do volume to volume, or like we just saw, we can go from grams to volume or volume to grams. So let's pause here and go to another video because this one's really long.